is CS50, and this is the end of week 5. And up until now, we've pretty much been taking for granted that there exists this compiler, Clang, that you've been invoking by way of this other tool called make, that somehow magically converts your source code into object code, the zeros and ones that your computer's CPU, central processing unit, actually understands. But it turns out there's been a number of steps going on underneath the hood in between input and output, and I'd like to propose that we flesh that out in a little more detail into these 4 steps, something called pre-processing, something called compiling, which we have seen, something called assembling, and something called linking. So up until now, in some of our programs, we've had sharp includes. More recently, we've had some sharp defines for constants. So it turns out that those things that are prefixed with the hash symbol or the pound symbol are preprocessor directives. That's just a fancy way of saying it's a line of code that's actually converted into something else before the computer even tries to convert your program into zeros and ones. For instance, sharp include standardio.h pretty much just means go ahead, grab the contents of the file standardio.h and paste them right there. So no zeros and ones at that point yet. It's really just a substitution, and that's done during the so-called pre-processing stage when you actually run Clang, or specifically make in most cases. So all of this has been happening for us automatically thus far. Then comes the compilation step, but we've been oversimplifying compilation. Compiling a program really means to take it from something like C, the source code we've been writing, down to something called assembly. Assembly language is a lower level language that thankfully we won't have much occasion to write this semester, but it's at the lowest level in the sense that you literally start writing add and subtract and multiply and load from memory and save to memory, the very basic instructions that a computer underneath the hood actually understands. Lastly, assembling takes that language to the zeros and ones that we've been describing thus far. And truly, lastly, there's the so-called linking phase, which we'll see in just a moment, which combines your zeros and ones with zeros and ones other people before you have created. So consider this super simple program. It was from week 1, just said hello world on the screen. We ran this through Clang, or we ran it through make, which ran Clang, and outputted at the time were some zeros and ones. But it turns out there's an intermediate step. If I go over here, oops, didn't want to see him yet. If I go over here to my appliance, and I open up hello.c, here's that same program. And what I'm going to do in my terminal window here is I'm going to run Clang rather than make, which automates all 4 of those steps for us. And I'm going to do Clang -S and then hello.c and then enter. And I get a blinking prompt again, which is good. And now in a slightly bigger window, I'm going to open up gedit in here, and I'm going to open up a file that turns out it's called hello.s. This contains that assembly language I referred to earlier, and this is what's called assembly language. Fairly low-level instructions that your Intel CPU or whatever it is that's inside understands, and MOV is for move, call is for calling a very low-level function, sub is for subtract. So when you have a particular CPU inside of your computer, what makes it distinct versus other CPUs on the market is which instructions it understands, and often how efficient it is, how fast it is at executing some of those instructions. Now, for more on this, you can take next fall CS61 at the college. But here we have, for instance, a few identifiers that might look familiar. Hello.c is the name of the program. .text, there's not much of interest there just now, but recall that the text segment, as of Monday, is where in memory your program actually ends up. So that's at least vaguely familiar there. Here, of course, is a mention of our main function. Scrolling down, these refer to things called registers, very small chunks of memory inside of your actual CPU. And if I scroll down even further, I see some sort of indirect mention of ASCII, and there indeed is that string, hello, comma, world. So long story short, this has been happening for you automatically underneath the hood all of this time. And what's been happening really is once you've run Clang, or by way of make, you're getting first from the source code, the so-called assembly language, then Clang is converting this assembly language down to zeros and ones. And this is the slide that we started our discussion in week 0 on, and then week 1 on. And then finally, those zeros and ones are combined with the zeros and ones from those libraries we've been taking for granted, like standardio, or the string library, or even the CS50 library. So to paint this picture more visually, if we have hello.c, and it, of course, uses the printf function to say hello world, the compilation step takes it down to that file we just saw, hello.s, even though that's typically deleted automatically for you. But that's the assembly code in the middle step. And then when we assemble the assembly language, so to speak, That's when you get those zeros and ones. So we've zoomed in effectively today on what we've been taking for granted, means going from source code to object code. But lastly, now that same picture, let's shove it over to the left-hand side and note that in the top there I mentioned standardio.h. That's a file that we've included in almost all of the programs we've written, and that's the file whose contents get copy-pasted, effectively atop your code. But it turns out that on a computer system somewhere, there's presumably a standardio.c file that someone wrote years ago that implements all of the functions that were declared in standardio.h. Now, in reality, it's probably not on your Mac or your PC or even in the CS50 appliance as raw C code. Someone already compiled it and included a .o file for object code, or a .a file, which refers to a shared library that's been pre-installed and pre-compiled for you. But suppose that there indeed exists on our computer standardio.c in parallel with Clang. Your code's being compiled and assembled. Standardio.c's code is being compiled and assembled, so that this very last step down here, we have to somehow link, so to speak, your zeros and ones with his or her zeros and ones into one simple program that ultimately is called just hello. So that's all of the magic that's been happening thus far. And we'll continue to take these processes for granted, but realize there's a lot of juicy details going on underneath there, and this is what makes your computer with Intel inside particularly distinct. So on that note, if you would like to join us for lunch this Friday, do go to the usual place, cs50.net/RSVP, 1:15 p.m. this Friday. And now a few announcements. So we have some good news and we have some bad news. We'll start with some good news here. All right, well, it's technically a holiday, so it's not so much a gift from us. But then the bad news, of course. Spent a lot of time on these animations. There will be a review session this coming Monday. It's going to be at 5:30 p.m. We will remind you of all of these details via email on the course's website in just a couple of days' time. It will be filmed and made available shortly thereafter, so if you can't make that Monday night slot, don't worry. Sections this coming week will also focus on review for the quiz. If your section is on Monday, which is indeed a university holiday, we will still meet in section. If you simply can't make that section because you're going away, that's fine. Attend a Sunday or Tuesday section, or tune in to Jason's section, which is available online. So, more bad news. So according to the syllabus, we have lecture next Friday. But, good news, all right, clearly I spent too much time on this. We'll cancel next Friday's lecture, so that will be a gift from us so that we can really have a nice respite in between this week and 2 weeks hence. So no lectures next week, just a tiny little quiz for which you should be getting increasingly excited. So, let's now turn our attention to something that is indeed more visual and more exciting, and to set the stage for what's going to be on the horizon in just a couple of weeks' time. After the first quiz, we'll turn the focus of our problem sets to another domain-specific problem, that of forensics, or security more generally. In fact, the tradition with this problem set is for me and one of the teaching fellows or CAs to walk across campus, taking some photographs of identifiable but non-obvious people, places, or things. Then every year I somehow manage to accidentally delete or corrupt the digital media card that's inside of our camera, but no big deal. I can go ahead and plug that into my computer. I can make a forensic image of it, so to speak, by copying the zeros and ones off of that memory card, whether it's an SD card or compact flash card or whatever you're familiar with, and then we can hand that out. And so the challenge ahead, among other things for you, will be to write C code that recovers a whole bunch of JPEGs for me. And revealed will be those people, places, or things. And we'll also talk in this problem set and in the days to come about graphics more generally. We've used them, of course, for breakout, but you've sort of taken for granted there exist these high-level notions of rectangles and ovals. But underneath the hood, there are pixels, and you've had to start thinking about those, or you will for PSET 4 have to think about the gap between your bricks, how quickly your ball is moving across the screen for breakout. So there is this notion of the dots on your screen that's come into play already. Now, what you see, though, is what you get on a computer screen. If you've ever watched some good or bad TV, odds are they pretty much treat the audience like technophobes who don't really know much about computing, and so it's very easy for the police detective to say, can you clean that up for me? Or enhance, right? Enhance is like the buzzword in most any crime-related show. And the reality is, if you take a very blurry picture of a suspect doing something bad, you cannot just enhance it. You cannot zoom in infinitely. You cannot see in the glint of someone's eye who committed that particular crime, despite the prevalence of this on TV. And so with that, let's motivate that upcoming problem set with a glimpse at some shows with which you might be familiar.
Okay. Now let's get a good look at you.
Hold it. Run that back.
Wait a minute. Go right.
There, freeze that.
Full screen.
Okay, freeze that.
Tighten up on that way.
Vector in on that guy by the back wheel.
Zoom in right here on this spot.
With the right equipment, the image could be enlarged and sharpened.
What's that?
It's an enhancement program.
Can you clear that up any?
I don't know. Let's enhance it.
Enhance section A6.
I enhance the detail, and
I think there's enough to enhance. Release it to my screen.
Enhance the reflection in her eye.
let's run this through video enhancement.
Edgar, can you enhance this?
Hang on.
I've been working on this reflection.
Someone's reflection.
Reflection.
There's a reflection of the man's face.
The reflection.
There's a reflection.
Zoom in on the mirror.
You can see a reflection.
Can you enhance the image from here?
Can you enhance him right here?
Can you enhance it?
Can you enhance it?
Can we enhance this?
Can you enhance it?
Hold on a second, I'll enhance.
Zoom in on the door.
Times 10.
Zoom.
Move in. More.
Wait, stop.
Stop.
Pause it.
Rotate us 75 degrees around the vertical, please.
Stop. And go back to the part about the door again.
Got an image enhancer that can bitmap?
Maybe we can use the Pradeep Sen method to see into the windows.
This software is state of the art.
The eigenvalue is off. With the right combination of algorithms.
He's taken illumination algorithms to the next level, and I can use them to enhance this photograph.
Lock on and enlarge the z-axis.
Enhance.
Enhanced.
Freeze and enhance.
So, problem set 5 is what lies ahead there. So, we'll soon get a better understanding of when and why you can or cannot enhance in that way. But first, let's return our attention to some of the building blocks we'll need to be able to tell that story. So recall that we drew this picture on Monday and a little bit last week, and this describes the layout of things in your computer's memory when running some program. The text segment up top, recall, refers to the actual zeros and ones that compose your program. There's below that some initialized or uninitialized data, which typically refers to things like constants or strings or global variables that have been declared in advance. There's the heap, but we'll come back to that in a bit. And then there's the stack, much like a stack of trays in the cafeteria. This is where memory gets layered and layered whenever you do what in a program? What is the stack used for? Yeah? Call a function. Anytime you call a function, it's given a sliver of memory for its local variables or its parameters. And pictorially, we see that with each successive function call, when A calls B, calls C, calls D, they get layered onto the stack. And within each of those slices of memory is essentially a unique scope for that function, which of course is problematic if you want to hand from one function to another a piece of data that you want it to mutate or change. So what was our solution to enabling a function represented by one stack frame to change the memory inside of another stack frame? How do those two talk to one another? So by way of pointers or addresses, which again just describe where in memory, by way of a specific byte number, the particular value can be found. So recall last time too, we continued this story and looked at a fairly buggy program. And this program's buggy for a few reasons, but the most worrisome one is because it fails to check what? Yeah, it fails to check the input, sorry? If it's more than 12 characters. So very smartly, when calling memcopy, which as the name suggests, just copies memory from its second argument into its first argument, the third argument, very smartly, is checked to make sure that you don't copy more than, in this case, the length of bar, number of characters, into the destination, which is this array C. But the problem is that what if C itself is not big enough to handle that? You're going to copy only the number of bytes that you've been given, but what if you actually have more bytes than you have room for? Well, this program very foolishly just blindly proceeds to take whatever it's given, HELLO, \0 is great if the string is short enough, like 5 chars, but if it's actually 12 characters or 1200 characters, we saw last time that you're just going to completely overwrite memory that doesn't belong to you. And worst case, if you overwrite that red portion there that we called the return address, this is just where the computer automatically, for you, behind the scenes, tucks away a 32-bit value that reminds it to what address it should return when foo, this other function, is done executing. It's a breadcrumb of sorts to which it returns. If you overwrite that, potentially, if you're the bad guy, you can potentially take over someone's computer, and you'll most certainly crash it in most cases. Now, this problem was only exacerbated as we started talking about memory management more generally. And malloc, for memory allocation, is a function that we can use to allocate memory when we don't know in advance that we might need some. So for instance, if I go back to the appliance here and I open up from last time hello2.c, recall this program here, which looked a little something like this. Just 3 lines, state your name, then string name on the left equals get string, and then we printed out the user's name. So this was a super simple program. To be clear, let me go ahead and make hello-2. I'm going to do /hello-2, state your name, David, enter, hello, David. It seems to work okay. But what's really going on underneath the hood here? First, let's peel back some layers. String is just a synonym, we've realized, for what? Char star. So let's make it a little more arcane, but more technically correct, that this is a char star, which means that name, yes, is a variable, but what name stores is the address of a char, which feels a little strange because I'm getting back a string. I'm getting back multiple chars, not a char. But of course, you only need the first char's address to remember where the whole string is, because why? How do you figure out where the end of the string is, knowing the beginning? The \0. So with those 2 clues, you can figure out both where the beginning and the end of any string are, so long as they're properly formed with that null terminator, that \0. But this is calling getString. And it turns out that getString all this time has been kind of cheating for us. It's been doing us a favor, to be sure, getting a string from the user. But where has that memory been coming from? If we go back to the picture here and apply the definition from just a moment ago, that the stack is where memory goes when functions are called. By that logic, when you call getString, and then I type in DAVID enter, where is DAVID \0 stored, based on the story we've told thus far? It would seem to be in the stack, right? When you call getString, you get a little slice of memory on the stack, so it stands to reason that DAVID \0 is stored there in the stack. But wait a minute, getString returns that string, so to speak, which means its tray from the cafeteria is taken off the stack. And we said last time that as soon as a function returns and you take that tray, so to speak, off the stack, what can you assume about the remnants of that memory? Right? I sort of redrew them as question marks because they effectively become unknown values. They can be reused when some next function is called. In other words, if we happen to be storing, and I'll draw a quick picture here of the stack, if we happen to be drawing the bottom of my memory segment, and we'll say that this is the slice of memory occupied by main and maybe argc and argv and anything else in the program, when getString is called, presumably getString gets a chunk of memory here, and then DAVID somehow ends up in this function. And I'm going to oversimplify, but let's assume that it's DAVID \0. So this many bytes are used in the frame for getString. But as soon as getString returns, we said last time that this memory over here all becomes effectively erased. And we can think of this now as question marks because who knows what's going to become of that memory. Indeed, I very often call functions other than getString, and as soon as I call some other function than getString, maybe not in this particular program we just looked at, but some other, surely some other function might end up being given this next spot in the stack. So it can't be that getString stores DAVID on the stack because I would immediately lose access to it. But we know that getString only returns what? It's not returning to me 6 characters. What is it truly returning, did we conclude last time? The address of the first. So somehow when you call getString, it's allocating a chunk of memory for the string that the user's typed and then returning the address of it. And it turns out that when you want a function to allocate memory in this way and return to the person who called that function, the address of that chunk of memory, you absolutely can't put it in the stack at the bottom because functionally it's just going to not become yours very quickly. So you can probably guess where we're probably going to toss it instead, the so-called heap. So between the stack and between the bottom of your memory's layout and the top of your memory's layout are a whole bunch of segments. One is the stack, and right above it is the heap. And the heap is just a different chunk of memory that's not used for functions when they are called. It's used for longer-term memory, when you want one function to grab some memory and be able to hang on to it without losing control over it. Now, you can perhaps immediately see that this is not necessarily a perfect design. As your program allocates memory on the stack, or as you call more and more functions, or as you allocate memory on the heap with malloc, as getString is doing, what clearly seems to be an inevitable problem? right? Like, the fact that these arrows are pointing at each other, like, does not bode well. And indeed, we could very quickly crash a program in any number of ways. In fact, I think we might have done this accidentally once, or if not, let's do it deliberately now. Let me go ahead and write super quickly a program called don't do this.c. And now I'll go in here and do sharp include standard.io.h. Let's declare a function foo takes no arguments, which is denoted as well by void. And the only thing foo is going to do is call foo, which probably isn't the smartest idea, but so be it. Int main void. Now the only thing main is going to do is call foo as well. And just for kicks, I'm going to go ahead here and say printf hello from foo. Okay, so if I didn't make any mistakes here, make don't do this dot slash, and let's do it in a bigger window, dot slash don't do this. Come on. Uh-oh. Apparently you can do this. Damn it. Okay, wait, stand by. Did we? No, we used it with make. I know, but I think we just deleted that. Yeah. Damn it. Solve this, Rob. What? It's very simple. Yeah, we turned optimization off. Okay, stand by. Now I feel better. Okay. All right, so let's recompile this. Make don't do this. So we might have to rename this to do this.c in just a moment. There we go. Thank you. Okay. So the fact that I was printing something out was actually just slowing down the process by which we would have reached that point. Okay, phew. So what is actually going on? And the reason there, just as an aside, is doing anything in terms of input and output tends to be slower because you have to write characters to the screen. It has to scroll. So long story short, had I actually not been so impatient, we would have seen this end result as well. Now that I got rid of the printfs, we see it right away. So why is this happening? Well, the simple explanation, of course, is that foo probably shouldn't be calling itself. Now, in general terms, this is recursion. And we thought a couple of weeks ago, recursion is good. Recursion is kind of this magical way of expressing yourself super succinctly, and it just works. But there was a key feature of all of the recursive programs we've talked about and looked at thus far, which was that they had what? A base case, which was some hard-coded case that said in some situations, don't call foo, which is clearly not the case here. So what is really happening in terms of this picture? Well, when main calls foo, it gets a slice of memory. When foo calls foo, it gets a slice of memory. When foo calls foo, it gets a slice, it gets a slice, it gets a slice. Because foo is never returning, we're never erasing one of those frames from the stack, so we're blowing through the heap, not to mention who knows what else, and we're overstepping the bounds of our so-called segment of memory, ergo segmentation faults. So the solution there is clearly don't do this, but the bigger implication is that, yes, there absolutely is some limit, even if it's not well defined, as to how many functions you can call in a program, how many times a function can call itself. So even though we did preach recursion as this potentially magical thing a couple of weeks ago for the sigma function, and when we get to data structures in CS50, you'll see other applications for it, it's not necessarily the best thing, because if a function calls itself, even if there's a base case, if you don't hit that base case for 1,000 calls or 10,000 calls, by that time, you might have run out of room on your so-called stack and hit some other segment of memory. So it, too, is a design trade-off between elegance and between robustness of your particular implementation. So there's another downside or another gotcha to what we've been doing thus far. When I called getString, let me go back into hello 2. Notice that I'm calling getString, which is returning an address, and we've claimed today that that address is from the heap, and now I am printing out the string at that address. But we've never called the opposite of getString. You know, we've never had to call a function like ungetString, where you hand back that memory. But frankly, we probably should have been, because if we keep asking the computer for memory by way of someone like getString, but never give it back, surely that too is bound to lead to problems whereby we run out of memory. And in fact, we can look for these problems with a new tool whose usage is a little cryptic to type, but let me go ahead and splash it up on the screen in just a moment. I'm going to go ahead and run Valgrind with a parameter whose first command line argument is the name of that program, hello-2. And unfortunately, its output is atrociously complex for no good reason. So we see all of that mess. David is state my name, so that's the program actually running. And now we get this output. So Valgrind is similar in spirit to GDB. It's not a debugger per se, but it's a memory checker. It's a program that will run your program and tell you if you have asked the computer for memory and never handed it back, thereby meaning that you have a memory leak. And memory leaks tend to be bad, and you as users of computers have probably felt this, whether you have a Mac or PC. I mean, have you ever kind of used your computer for a while, not rebooted in several days, or you've just got a lot of programs running, and the damn thing kind of slows to a grinding halt, or at least it's super annoying to use because everything just got super slow. Now, that can be for any number of reasons. It could be an infinite loop, a bug in someone's code, or more simply, it could mean that you're using more memory, or trying to, than your computer actually has. And maybe there's a bug in some program that keeps asking for memory. Browsers, for years, were notorious for this, asking for more and more memory, but never handing it back. Surely, if you only have a finite amount of memory, you can't ask infinitely many times for some of that memory. And so we see here, even though, again, Valgrind's output is unnecessarily complex to glance at first, this is the interesting part. Heap summary in use at exit. So here's how much memory was in use in the heap at the time my program exited. Apparently 6 bytes in one block. So I'm going to wave my hands at what a block is. Think of it as just a chunk, a more technical word for chunk. But 6 bytes. Why? What are these 6 bytes that were still in use? Exactly, DAVID \0, 5-letter name plus the null terminator. So this program, Valgrind, noticed that I asked for 6 bytes, apparently, by way of getString, but never gave them back. And in fact, this might not be so obvious if my program isn't 3 lines, but it's 300 lines. So we can actually give another command line argument to Valgrind to make it more verbose. It's a little annoying to remember, but if I do, let's see, leak, was it leak? Even I don't remember what it is offhand. Leak check equals full. Yep, thank you. Leak check equals full. Enter. Same program is running. Type in David again. Now I see a little more detail, but below the heap summary, which is identical to before. This is kind of nice. Now Valgrind is actually looking a little harder at my code, and it's saying that apparently malloc at line, if we zoom out, at line, we don't see what line it is, but malloc is the first culprit. There's a bug in malloc. It's right? Okay, no, right? Like I called getString. getString apparently calls malloc. So what line of code is apparently at fault for having allocated this memory? Yeah, let's assume that whoever wrote malloc has been around for long enough that it's not their fault. It's probably mine. getString in cs50.c, so that's a file somewhere on the computer, in line 286 seems to be the culprit. Now let's assume that cs50 has been around for a decent amount of time, so we too are infallible. And so it's probably not in getString that the bug lies, but rather in hello-2.c, line 18. So let's take a look at what that line 18 was. Oh, somehow this line, isn't necessarily buggy per se, but it is the reason behind that memory leak. So super simply, what would intuitively be the solution here? If we're asking for memory, we're never giving it back, and that seems to be a problem because over time, my computer might run out of memory, might slow down, bad things might happen. Well, what's the simple intuitive solution? Just give it back. How do you free up that memory? Well, thankfully, it's quite simple to just say free name. And we've never done this before, but you can essentially think of free as the opposite of malloc. Free is the opposite of allocating memory. So now let me recompile this, make hello-2. Let me run it again, hello-2, David. So it seems to work in exactly the same way. But if I go back to Valgrind and rerun that same command on my newly compiled program, typing in my name as before, nice, heap summary, in use at exit, 0 bytes and 0 blocks. And this is super nice. All heap blocks were freed. No leaks are possible. So coming up, not with problem set 4, but with problem set 5, the forensics and onward, this too will become a measure of the correctness of your program, whether or not you have or don't have memory leaks. But thankfully, not only can you reason through them intuitively, which is arguably easy for small programs, but harder for larger programs, Valgrind for those larger programs can help you identify the particular problem. But there's one other problem that might arise. Let me open up this file here, which is, again, a somewhat simple example, but let's focus on what this program does. This is called memory.c. We'll post this later today in the zip of today's source code. And notice that I have a function called f that takes no arguments and returns nothing. In line 20, I'm apparently declaring a pointer to an int and calling it x. I'm assigning it the return value of malloc. And just to be clear, how many bytes am I probably getting back from malloc in this situation? Probably 40. Where do you get that from? Well, if you recall that an int is often 4 bytes, at least it is in the appliance, 10 times 4 is obviously 40. So malloc is returning an address of a chunk of memory and storing that address ultimately in x. So to be clear, what then is happening? Well, let me switch back to our picture here. Let me not just draw the bottom of my computer's memory. Let me go ahead and draw the whole rectangle that represents all of my RAM. We'll say that the stack is on the bottom, and there's the text segment and the uninitialized data, but I'm just going to abstract those other things away as ... I'm just going to refer to this as the heap at the top. And then at the bottom of this picture, to represent main, I'm going to give it a slice of memory on the stack. For f, I'm going to give it a slice of memory on the stack. And now I got to consult my source code again. What are the local variables for main? Apparently nothing, so that slice is effectively empty, or not even as big as I've drawn it. But in f, I have a local variable, which is called x. So I'm going to go ahead and give f a chunk of memory, calling it x. And now, malloc of 10 times 4, so malloc 40, where is that memory coming from? We've not drawn a picture like this before, but let's suppose that it's effectively coming from here. So 1, 2, 3, 4, 5, and now I need 40 of these, so I'll just do ... to suggest that there's even more memory coming back from the heap. Now, what's the address? Let's choose our arbitrary address as always, 0x123, even though it's probably going to be something completely different. That's the address of the first byte in memory that I'm asking malloc for. So in short, once line 20 executes, what is literally stored inside of x here? 0x123. 0x123. And the 0x is uninteresting. It just means here's a hexadecimal number. But what's key is that what I've stored in x, which is a local variable, but its data type, again, is an address of an int, well, I'm going to store 0x123. But again, if that's a little too complicated unnecessarily, if I scroll back, we can abstract this away quite reasonably and just say that x is a pointer to that chunk of memory. Okay, so now the question at hand is the following. Line 21, it turns out, is buggy. Why? Sorry? It doesn't have, say that once more? Well, it doesn't free, so that's a second bug. So there's one other bug specifically, though, at line 21. Exactly. This simple line of code is just a buffer overflow, a buffer overrun. A buffer just means a chunk of memory, but that chunk of memory is of size 10 integers, which means if we index into it using the syntactic sugar of array notation, the square brackets, you have access to x bracket 0, x bracket 1, x bracket ... x bracket 9 is the biggest one. So if I do x bracket 10, where am I actually going in memory? Well, if I have 10 ints, let's actually draw all of these out here. So that was the first 5. Here's the other 5 ints. So x bracket 0 is here, x bracket 1 is here, x bracket 9 is here, x bracket 10 is here, which means I am telling in line 21 the computer to put the number where? The number 0 where? Well, it's 0, yes, but just the fact that it's 0 is kind of a coincidence. It could be the number 50 for all we care, but we're trying to put it at x bracket 10, which is where this question mark is drawn, which is not a good thing. This program might very well crash as a result. Now, let's go ahead and see if this is indeed what happens. Make memory, since the file is called memory.c. Let's go ahead and run the program, memory. So we got lucky, actually, it seems. We got lucky. But let's see if we now run Valgrind. At first glance, my program might seem to be perfectly correct, but let me run Valgrind with the leak check equals full on memory. And now when I run this, interesting, invalid write of size 4 at line 21 of memory.c. Line 21 of memory.c is which one? Oh, interesting. But wait, size 4, what is that referring to? I only did one write, but it's of size 4. Why is it 4? It's because it's an int, which is, again, 4 bytes. So Valgrind found a bug that I, glancing at my code, didn't. And, maybe your TF would or wouldn't. But Valgrind for sure found that we've made a mistake there, even though we got lucky. And the computer decided, I'm not going to crash just because you touched 1 int's worth of memory that you didn't actually own. Well, what else is buggy here? Address, this is a crazy looking address in hexadecimal. That just means somewhere in the heap is 0 bytes after a block of size 40 is allocated. Let me zoom out here and see if this is a little more helpful. Interesting. 40 bytes are definitely lost in loss record 1 of 1. Again, more words than is useful here, but based on the highlighted lines, where should I probably focus my attention for another bug? Looks like line 20 of memory.c. So if we go back to line 20, that's the one that you identified earlier. And it's not necessarily buggy, but we haven't reversed its effects. So how do I correct at least one of those mistakes? What could I do after line 21? I could do free of x so as to give back that memory. And how do I fix this bug? I should definitely go no farther than 0. So let me try and rerun this. Sorry, definitely go no farther than 9. Make memory. Let me rerun Valgrind in a bigger window. And now, look, nice. All heap blocks were freed. No leaks are possible. And up above here, there's no mention anymore of the invalid write. Just to get greedy, and let's see if another demonstration does not go as intended. I did get lucky a moment ago. And the fact that this is 0 is perhaps unnecessarily misleading. Let's just do 50, a somewhat arbitrary number. Make memory. /memory, still get lucky. Nothing's crashing. Suppose I just do something really foolish, and I do 100. Let me remake memory, /memory. Got lucky again. About 1,000 ints beyond roughly where I should be. Make memory. Damn it. OK. Let's not mess around anymore. Rerun memory. There we go. All right. So apparently, if you index 100,000 ints beyond where you should have been in memory, bad things happen. So this is obviously not a hard, fast rule. I was kind of using trial and error to get there. But this is because, long story short, your computer's memory is also divided into these things called segments. And sometimes the computer actually has given you a little more memory than you asked for. But for efficiency, it's just easier for it to get more memory, but only tell you that you're getting a portion of it. And if you get lucky sometimes, therefore, you might be able to touch memory that doesn't belong to you. You have no guarantee that what value you put there will stay there, because the computer still thinks it's not yours, but it's not necessarily going to hit another segment of memory in the computer and induce a mistake like this one here. All right, any questions then on memory? Now, all right, let's take a look here then at something we've been taking for granted for quite some time, which is in this file called cs50.h. So this is a file. These are just a whole bunch of comments up top. And you might have looked at this if you poked around on the appliance. But it turns out that all this time, when we used to use string as a synonym, the means by which we declared that synonym was with this keyword typedef for type definition. And we're essentially saying make string a synonym for char star. That's the means by which the staff created these training wheels known as the string. Now here's just a prototype for getChar. We might not have seen it before, but that's indeed what it does. GetChar takes no arguments, returns a char. GetDouble takes no arguments, returns a double. GetFloat takes no arguments, returns a float, and so forth. And getInt is in here, getLong is in here, and getString is in here, and that's it. This purple line is another preprocessor directive because of the hashtag at the beginning of it. All right, so now let me go into cs50.c, and we won't dwell too long on this, but just to give you a glimpse of what's been going on all this time, let me go to, let's do getChar. So getChar is mostly comments, but it looks like this. So this is the actual function getChar that we've been taking for granted exists. And even though we haven't used this one that often, if ever, it's at least relatively simple, so it's worth taking a quick look at here. So getChar has an infinite loop, deliberately so, apparently. It then calls, and this is kind of a nice reuse of code we ourselves wrote, it calls getString. Because what does it mean to get a char? Well, you might as well try to get a whole line of text from the user and then just look at one of those characters. In line 60 here is a little bit of a sanity check. If getString return null, let's not proceed. Something went wrong. Now, this is somewhat annoying but conventional in C. Char max probably represents what, just based on its name? It's a constant. It's like the numeric value of the biggest char you can represent with 1 byte, which is probably the number 255, which is the biggest number you can represent with 8 bits starting from 0. So I use this in this function when writing this code only because if something goes wrong in getChar, but its purpose in life is to return a char, you need to somehow be able to signal to the user that something went wrong. We can't return null. It turns out that null is a pointer, and again, getChar has to return a char. So the convention in C, if something goes wrong, is you, the programmer, or in this case, me with the library, I had to just decide arbitrarily, if something goes wrong, I'm going to return the number 255, which truly means that the user cannot type the character represented by the number 255, because we had to steal it as a so-called sentinel value to represent a problem. Now, it turns out that the character 255 is not something you can type on your keyboard, so it's no big deal. The user doesn't notice that I've stolen this character. But if you ever see in man pages on a computer system some reference to an all-caps constant like this that says, in cases of error, this constant might be returned, that's all some human did years ago, is arbitrarily decided to return this special value and call it a constant in case something goes wrong. Now, the magic happens down here. First, I'm declaring in line 67 2 characters, C1 and C2. And then in line 68, there's actually a line of code that's reminiscent of our friend printf, given that it does have %Cs and quotes. But notice what's happening here. scanf means string scan, scan a formatted string, ergo scanf. What does that mean? It means you pass to scanf a string, and line is whatever the user typed in. You pass to scanf a format string like this that tells scanf what are you hoping the user has typed in. You then pass in the addresses of 2 chunks of memory in this case, because I have 2 placeholders. So I'm going to give it the address of C1 and the address of C2. And recall that if you give a function the address of some variable, what's the implication? What can that function do as a result of giving it the address of a variable as opposed to the variable itself? It can change it, right? If you hand someone a map to a physical address, they can go there and do whatever they want at that address. Same idea here. If we pass to scanf the address of 2 chunks of memory, even these tiny little chunks of memory, C1 and C2, but we tell it the address of them, scanf can change it. So scanf's purpose in life, if we read the man page, is to read what the user typed in, hope for the user having typed in a character and maybe another character, and whatever the user typed, the first character goes here, the second character goes here. Now, as an aside, this, and you would only know this from the documentation, the fact that I put a blank space there just means that I don't care if the user hits the space bar a few times before he or she types a character. I'm going to ignore any white space. So that I know from the documentation. The fact that there's a second %C followed by white space is actually deliberate. I want to be able to detect if the user screwed up or didn't cooperate. So I'm hoping that the user only typed in 1 character. Therefore, I'm hoping that scanf is only going to return the value 1, because again, if I read the documentation, scanf's purpose in life is to return to you the number of variables that were filled with user input. I passed in 2 variables addresses, C1 and C2. I'm hoping, though, that only one of them gets filled, because if scanf instead returns 2, what's presumably the implication logically? That the user didn't just give me 1 character like I told him or her. They probably typed at least 2 characters. So if I instead did not have this second %C, I just had 1, which frankly would be the more intuitive approach, I think, at first glance, you're not going to be able to detect if the user has been giving you more input than you actually wanted. So this is an implicit form of error checking. But notice what I do here. Once I'm sure that the user gave me 1 character, I free the line, doing the opposite of getString, which in turn uses malloc, and then I return C1, the character that I hoped that the user provided and only provided. So a quick glimpse only, but any questions on getChar? We'll come back to some of the others. Well, let me go ahead and do this. Suppose now, just to motivate our discussion in a week plus time, this is a file called structs.h. And again, this is just a taste of something that lies ahead. But notice that a lot of this is comments, so let me highlight only the interesting part for now. Typedef, there's that same keyword again. Typedef we use to declare string as a special data type. you can use typedef to create brand new data types that didn't exist when C was invented. For instance, int comes with C, char comes with C, double comes with C, but there's no notion of a student. And yet it would be pretty useful to be able to write a program that stores in a variable a student's ID number, their name, and their house. In other words, 3 pieces of data, like an int and a string and another string. With typedef, what's pretty powerful about this, and the keyword struct for structure, you, the programmer in 2013, can actually define your own data types that didn't exist years ago, but that suit your purposes. And so here in lines 13 through 19, we're declaring a new data type, like an int, but calling it student. And inside of this variable is going to be 3 things: an int, a string, and a string. So you can think of what's really happened here, even though this is a bit of a simplification for today. A student is essentially going to look like this. It's going to be a chunk of memory with an ID, a name field, and a house field. And we'll be able to use those chunks of memory and access them as follows. If I go into struct0.c, here's a relatively long but following a pattern of code that uses this new trick. So first, let me draw your attention to the interesting parts up top. Sharp defines students3, declares a constant called students, and assigns it arbitrarily the number 3, just so I have 3 students using this program for now. Here comes main. And notice, how do I declare an array of students? Well, I just use the same syntax. The word student is obviously new, but student, class, bracket, students. So unfortunately, there's a lot of reuse of terms here. This is just a number, so this is like saying 3. Class is just what I wanted to call the variable. I could have called it students, but class, this is not a class in an object-oriented Java kind of way. It's just a class of students. And the data type of every element in that array is student. So this is little different from saying something like this. It's just, I'm saying give me 3 students and call that array class. All right, now here's a for loop. This guy's familiar. Iterate from 0 on up to 3. And here's the new piece of syntax. The program's going to prompt me, the human, to give it a student ID, which is an int. And here's the syntax with which you can store something in the ID field at location class bracket I. So this syntax is not new. This just means give me the ith student in the class. But this symbol is new. Up until now, we've not used dot, at least in code like this. This just means go to the struct known as a student and put something there. Similarly, in this next line, 31, go ahead and put whatever the user types for a name here. And what they do for a house, same thing. Go ahead and put it in .house. So what does this program ultimately do? You can see a little teaser there. Let me go ahead and do make structs0 /struct0, student's ID 1, say David, Mather, student ID 2, Rob, Kirkland, student ID 3, Lauren, Leverett. And the only thing this program did, which is just completely arbitrary, is I wanted to do something with this data now that I'd taught us how to use structs, is I just had this extra loop here. I iterate over the array of students. I used our perhaps now familiar friend string compare, strcomp, to check, is the ith student's house equal to Mather? And if so, just print something arbitrarily like, yes, it is. But again, just giving me opportunities to use and reuse this new dot notation. So who cares, right? Coming up with a student program is somewhat arbitrary, but it turns out that we can do useful things with this. For instance, as follows. This is a much more complicated struct in C. It's got a dozen or more fields, somewhat cryptically named. But if you've ever heard of a graphics file format called bitmap, BMP, it turns out that the bitmap file format pretty much looks like this. This is a stupid little smiley face. It's a small image that I've zoomed in on pretty big so that I could see each of the individual dots or pixels. Now, it turns out we can represent a black dot with, say, the number 0 and a white dot with the number 1. So in other words, if you want to draw a smiley face and save that image in a computer, it suffices to store 0s and 1s that look like this, where again 1s are white and 0s are black. And together, if you effectively have a grid of 1s and 0s, you have a grid of pixels. And if you lay them out right, you have a cute little smiley face. Now, the bitmap file format, BMP, is effectively that underneath the hood, but with more pixels so that you can actually represent colors. But when you have more sophisticated file formats like BMP and JPEG and GIF, with which you might be familiar, those files on disk typically not only have 0s and 1s for the pixels, but they have some meta data as well. Meta in the sense that it's not really data, but it's useful to have. So these fields here are implying, and we'll see this in more detail in PSET 5, that before the zeros and ones that represent the pixels in an image, there's a bunch of metadata like the size of the image and the width of the image. And notice I'm plucking off some arbitrary things here, width and height, bit count, and some other things. So there's some metadata in a file. But by understanding how files are laid out in this way, you can actually then manipulate images, recover images from disk, resize images. But you can't necessarily enhance them. I needed a photograph, so I went back to RJ here, who you saw on the screen quite some time ago. And if I open up Keynote here, this is what happens if you try to zoom in and enhance RJ. He's not getting any better, really. Now, Keynote is kind of blurring it a little bit, just to gloss over the fact that RJ does not get particularly enhanced when we zoom in. And if I do it this way, see the squares? Yeah, you can definitely see the squares on the projector. That's what you get when you enhance. But understanding how RJ, or the smiley face, is implemented will let us actually write code that manipulates these things. And I thought I'd end on this note with 55 seconds of an enhance that's, I dare say, rather misleading.
He's lying. About what? I don't know.
So what do we know?
That at 9:15, Ray Santoya was at the ATM.
So the question is, what was he doing at 9:16?
Shooting the 9mm at something. Maybe he saw the sniper.
Or was working with him.
Wait. Go back one.
What do you see?
Bring his face up. Full screen.
His glasses.
There's a reflection.
That's the Nuevitas baseball team. That's their logo.
And he's talking to whoever's wearing that jacket.
This will be Problem Set 5. We will see you next week.
At the next CS50,